So this is an extension of what we did with our real number sets. We're going to talk a little bit about some of the operations that are used, particularly when we're working with irrational numbers. But you'll see in front of you on my screen just a list of the vocab that we should be, at the end of this video, comfortable with. So why don't we just knock out the ones that we already covered? For example, we touched on natural numbers and integers. We talked about irrational numbers, and we also worked a little bit with whole numbers. One branch off of these is this term right here, and it's an element. So let's just talk about what that means by definition. So an element of a set is a number that belongs to a set. Let's do an example. So we've got, for example, the set of integers. And we know the set of integers contains all of these elements, and it goes on infinitely. So we know that -7, for example. -7 is an integer because it belongs to the integer set. So we could say that -7 is an element of the integer set. We could say 53 is an element of the integer set. And that looks like this notation. It looks like a sort of stretched out E. So here is one example of the notation we could say. So -7 belongs to the set of integers. And as you know, we could say that for a couple of other different sets as well. Belongs to the set of rational numbers. So that by definition is what an element is relative to a set. And then we start talking about the next few terms, which overlap. Those are these 4. These are fun. So let's define. I'm going to write out. Let's say we've got root 13. So there are some special things going on here. Let's define them all. So if I have the square root of 13, this little symbol here, and what I'm referring to is this, is referred to as the actual radical. So that operation, that notation is telling us to take the square root of that number that's inside the radical. Ooh, well, what is that number inside the radical? That, people, is called the radicand. So this notation, sort of by itself, is defined as the square root. And without getting too much into the weeds, it's referred to as a square root even though the number here is not written. There's no number written right here. You have seen, or maybe you will see if you haven't seen it before, different kinds of roots. There are cube roots, so you might see something that looks like this. And this is actually telling you to take the cube root. There is we've got fourth roots. I can say the fourth root of 2. And by doing so, these two numbers, that notation and that placement is called the index. But for our purposes, when nothing is written, there is no index number written there, then we're working with square roots. It's the same idea as if we had, like x squared plus 3x. There's no number written in front of the x squared, so it's understood that it's 1. Same here. If there's no number written right there on the outside of that radical, it's implied that we're taking the square root. Later in another unit, we're going to focus on simplifying radicals, particularly square roots and cube roots. But for now, our purposes is to focus on what perfect squares are and how they tie into our radicals. So if we're defining a perfect square, we would say that a perfect square is the product of a rational number multiplied to itself. Our special ones are really the whole number perfect squares, meaning, and I think you've seen this notation before, and we typically go up until 12, but I think once we at least identify, let's maybe do the top 7. Oh, I don't like eliminating the others, but let's do it. Just for clarity's sake, these are all perfect squares because I'm taking this number, this rational number, and I'm multiplying it to itself. So 0 squared is 0. 1 squared is 1. 2 squared, we can just keep filling these out, right? And we're getting these by saying 2 times 2, 3 times 3, 4 times 4. So we've got 25, we've got 36, we've got 49, and then we would continue to do this with 8 until, and I would suggest going to 12 or at least 13. We've got to have those on lockdown. And this is useful when we've got these perfect squares. It's like magic. This implies that if I take, I'm going to highlight these. If I take these numbers that are on this or in this right column and I take the square root of them, it's going to result in, let's color code, the blue column without the square. So when we're working with these perfect squares and with radicals, when we see, I'm going to use x, and x for now could represent any one of these positive numbers that's being squared, right? I want us to sort of identify that this radical, that's the radical, that's the square root, and this square, the square and the square root are enemies, and they fight each other and they cancel each other out. So this square root undoes the square. It's actually called an inverse operation. It's like one does something and the other one reverses it. It's like, not happening. So for example, if I had, I'll start with 0, the square root of 0, I know that 0 is 0 squared, and there's that fight. They're fighting it out and they undo each other, which leaves us with 0. Now, let's look at, one's going to do the same thing, but let's look at the second. Let's look at 2 squared equaling 4. So if we had, for example, root 4, we know that 4 is a perfect square and can be treated as 2 squared. 2 squared is 4. Square root, square, enemies. Undo each other, leaving us with 2. Square root 9, we repeat this process. We know 9 is a perfect square, and we know fight it out, fight it out. They cancel each other out, leaving us with 3. And so you'll notice it's the same idea. So you might think this second part, like this is like your thought bubble, like, oh, this is what's going on inside your brain. But then you know that those two eliminate, choo, choo, and that just leaves us with 4. And then you'll get faster at it and you'll say 25 is 5 squared, and the square root and the square undo each other. That leaves us with 5. Here's one that you haven't seen. What are you thinking? Well, I hope you're thinking that 81 is 9 squared, and that radical and that squared cancel. And so root 81 leaves us with 9.